సార్
హలో హలో
సార్
చెప్పండి చెప్పండి ఎవరు
సార్ వాయిస్ అసలు రావట్లేదు
సార్ ఇప్పుడు దాకా
వాయిస్
వీడియో
రావు.
ప్లే లేదు సార్.
వీడియో కూడా అసలు ప్లే కాలేదు సార్.
హాఫ్ అన్ అవర్ ఆల్మోస్ట్ 11 minutes అయిపోయిందండి. మీరు ఇప్పుడు దాకా ఏం
అదే
చేస్తున్నారు?
ప్లే అవ్వలేదు సార్ అసలు.
అసలు ఏం ఫస్ట్ పేజ్ లోనే ఉండిపోయింది సార్. అది 0.2 seconds దగ్గర.
చెప్పాలి కదా, గమ్ముకుంటే ఎలాగా? నాకెలా తెలుస్తుంది అది? Is it audible now?
Yes, sir.
Is it audible now?
నో సార్.
Yes, sir.
Now?
స్లైడ్స్ కనిపిస్తున్నాయి కానీ మీ వాయిస్ వినిపించట్లేదు సార్.
నా వాయిస్ కదమ్మా, నేను రికార్డ్ చేసింది అది.
అదే సార్ వినిపించట్లేదు.
ఏ అమరావతి వినిపించిందా?
లేదు సార్.
The covariance.
Now,
So
now
coming to the first one, that is joint central moments. So here we are considering two random variables. We are not considering multiple random variables. We are initially considering two random variables, that is x and y. Then the x
వినిపిస్తుందండి?
ఎస్ సార్, వినిపిస్తుంది సార్.
expected value of the function g of x comma y. In the previous one we have
కెన్ ఐ ప్లే ఫ్రమ్ స్టార్టింగ్ నుంచి ప్లే చేయమంటారండి?
ఎస్ సార్.
ఎస్ సార్.
Good morning students, welcome to another lecture on probability theory and stochastic process.
Audible?
Yes sir.
Was that audible?
సార్. ఎస్ సార్.
In the previous session we have discussed about statistical independence of random variables, central limit theorem, in that equal functions and unequal functions.
Is it audible?
And functions of joint random variables.
Yes, sir.
And joint moments about origin, orthogonality theorem problems, and correlation properties. So in this today's class we are going to discuss about joint central moments and covariance, correlation coefficient, properties of covariance. That means by the end of this lecture you all are going to know about these four topics, that is joint central moments, how these joint central moments will be calculated, and the covariance, how we are going to calculate the covariance and correlation coefficients along with the properties of the covariance. So coming to the first one, that is joint central moments. So here we are considering two random variables. We are not considering multiple random variables. We are initially considering two random variables, that is x and y. Then the expected value of the function g of x comma y. In the previous one we have discussed about expected value of a function e of x comma y, like that we have written. So the expected value of the function g of x comma y can be written as small x minus x complement capital X complement whole to the power of n into small y minus capital Y complement whole to the power of k, are called as the joint central moments. And we are going to mathematically represent that one as mu n k is equals to expected value of small x minus capital X complement whole to the power of n into small y minus capital Y whole to the power of k, capital Y complement whole to the power of k, and which can be represented as integral minus infinity to infinity for x value and integral minus infinity to infinity for y value, small x minus capital X complement whole to the power of n into small y minus capital Y complement whole to the power of k into fxy of x comma y into dx dy, which will be equals to 0. So where n and k are the positive integers, where n and k are the positive integers, and the order of the moment can be calculated or can be represented by making use of this, the summation, by making use of the summation, that is n plus k is the order of the particular moment. Okay, so in order to represent this suppose 0th order or first order or second order or nth order, so they have we are going to represent those things in this manner. So So the zeroth order of the central moment theorem is, we can write it as mu of 0 0 here. X value and y value are 0 0. So which will be equals to E of 1, and the output complete value will be equals to 1. So, and the first order moment can be written in two ways, that is mu of 1 comma 0 and mu of 0 comma 1. Here 1 comma 0 in sense we have only x value, and here y comma 0 comma 1 means we have only y value. So we are going to write this one in this manner. E of 1 comma 0 is equals to, sorry, mu of 1 comma 0 equals to E of small x minus x complement, small x minus capital X complement, which will be equals to E of small capital X complement minus E of capital X minus x complement, which will be equals to 0. In the same sense, mu of 0 1 is equals to E of small y minus y complement, which will be equals to capital E of expected value of capital Y complement minus expected value of capital Y complement, which is equals to 0. And the second order, here we have written zeroth order and we have written first order. Second order, there will be a somewhat slightly change in the second order. See here, we can write like this: mu of 2 comma 0, mu of 0 comma 2, and mu of 1 comma 1. Here in mu of 2 comma 0 we have only x values. Mu of 0 comma 2 we have only y values. Mu of 1 1 we have both x and y values. So see here, mu of 2 comma 0 is equals to expected value of small x minus capital X complement whole square, which will be equals to sigma x square. And the same sense, mu of 0 to equals to mu of 0 to is equals to E of y minus capital Y complement whole square, which will be equals to sigma y square. And in the other form, this is called a covariance. In the other form, we are going to write this one as mu of 1 1 equals to E of small x minus x complement whole to the power of 1 into small y minus y complement whole to the power of 1. By adding this to 1 plus 1, which will be equals to 2, and we can also call it as a second order one. So this mu of 1 1 is equals to E of x minus x complement whole to the power of 1 into y minus y complement whole to the power of 1 is equals to sigma xy. We can also replace mu of 1 1 as sigma xy. So see here, for n random variables, the joint central moments are defined as u of n1, n2, so on nn equals to expected value of small x1 minus capital X1 complement whole to the power of n1 అలాగా n వరకు తీసుకోండి n. Okay, next one is x2 minus small x2 complement whole to the power of n2, so on xn minus capital Xn complement whole to the power of n. And it can also be written as integral minus infinity to infinity to integral minus infinity to infinity n times. Why? Because we have taken n random variables, that's why we are integrating in n times. Okay, integral minus infinity to infinity, so on integral minus infinity to infinity x1 minus x1 complement whole to the power of n1 into x2, so on xn minus xn complement whole to the power of nn into f(x1) f suffix x1 of f suffix x1 x2 x3 so on xn of x1 x2 x3 so on xn of dx1 dx2 so on dxn. And the order of the joint central moment, so the order of this moment, n random variable moment, will be equals to small n1 plus small n2 plus so on small nn. And coming to the covariance, so consider two random variables x and y. The second order joint central moment mu11, see here we have already seen that one, mu11 is equals to sigma xy. So here we are considering that one. Mu11 is called the covariance of x and y, and it can be expressed as, see here, cxy, covariance of xy, which will be equals to sigma xy, which will be equals to mu11 which will be equals to expected value of small x minus capital X complement into small y minus capital Y complement. So దీని value ఎలా రాసుకున్నానా? You can also write this value as cxy is equals to integral minus infinity to infinity integral minus infinity to infinity small x minus capital X complement whole to the power of 1 into small y minus capital Y complement whole to the power of 1 into fxy of x comma y into dx dy. Okay, so this is for nth order, or this is here, this is covariance is for second order covariance, right? So coming to the discrete random variable, for example, we are taking any value in between small n to capital N, 1 or 1 to capital N, then for discrete random variables the covariance will be like this. For discrete random variables of x and y, cxy is equals to sigma n is equals to 1 to n, this value is for x, and sigma k is equals to 1 to capital K, and this value is for y of xn minus xn complement whole to the power of 1 into small yk minus capital yk complement whole to the power of 1 into p of probability of capital Xn into yk. Okay, so coming to the correlation coefficient for the random variables x and y, the normalized second order central moment. Okay, the normalized order ఎలా ఉంటుంది అనేది చెప్తానండి. The normalized second order central moment is called the correlation coefficient, and it is denoted by rho nana, it is rho, okay, rho, and is given by rho is equals to mu of 1 this is second order divided by square root of, I repeat, mu of 1 this is a covariance, okay, mu of 1 that means here x is equals to 1 and y is equals to 1 divided by mu of 2 that means here x is equals to 2 and y is equals to 0 into mu of 0 to, that is x is equals to 0 and y is equals to 2. So we can also write this one as mu of 2 and mu of 0 can be also written as sigma x square into sigma y square. So mu of 1 can also be written as c11 or cxy. So cxy and mu of 20 can be written as sigma x square, mu of 02 can be written as sigma y square. So cxy, which will be equals to cxy, here square and root get cancel, that means sigma x into sigma y. So cxy can also be written as sigma xy, so sigma xy by sigma x into sigma y. So which can also be written as sigma xy can also be written as e of x minus x complement into e of y minus y complement by sigma x into sigma y. So see the properties of our rho. The range of the correlation coefficient must always lies in between -1 and +1. So it has to be within these two values only, -1 and +1. Okay, and if x and y are independent, then this rho value will be equals to 0. Okay, if the correlation between x and y is perfect, that means these two values are equal, then the rho value will be equals to plus or minus 1, that means either it is -1 or it is +1. So if x is equals to 1, that means the random variables what we have taken, both values are equal, then the rho value is equals to 1, there is no chance of -1 and all these things. Okay, so coming to the next one, properties of the covariance. First, see the first one. If x and y are two random variables, then the covariance is cxy is equals to rxx minus x complement into y complement. We need to prove that. So what they have given, x and y are two random variables then we can also write as cxy is equals to, as we have already known, cxy is equals to e of x minus x complement into e of y minus y complement. So multiply this one, e of x into y minus x complement into y minus y complement into x minus x complement y complement. We have written, we have multiplied these two things. Okay, we have taken expected value as common, x into y and x complement into y. Next y complement into x and x complement y complement. So we have written separately, that is Pratidani, each and every literal has been written separately, e of x y minus e of x complement y minus e of x y complement or y complement x minus e of x complement y complement. Okay, so e of x complement y complement, if these both two are equal, then the expected value will be equals to 1. We know that in the previous slide we have discussed about that one, that is e of x y minus x complement into e of y minus y complement into e of x minus x complement y complement into e of 1. Okay, so see here, e of xy minus x complement y complement minus y complement x plus x complement y complement. Okay, so it will be equals to e of xy minus x complement y complement. Okay, so coming to the next one, if two random variables x and y are independent, then the covariance is 0, that is cxy is equals to 0, but the covariance is not true. Sorry, but the converse is not true. As we have already known that independent variables కనుక అయితే c of xy is equals to 0 అవుతుంది అంటున్నాడు, but then if you remove converse that one, it will not be true function. We need to prove that. So consider two random variables x and y. If x and y are independent, we know that e of xy is equals to e of x into e of y, right? That is e of xy is equals to product of individual expected values, that is e of x into e of y, and the covariance of x and y is cxy is equals to rxy into x complement y complement. In the previous session we have seen cxy is equals to rxy minus x complement y complement. Okay, that is rxy can also be written as e of xy, rxy can also be written as e of xy minus x complement y complement, and e of xy is equals to e of x into e of y minus x complement y complement. So e of x into e of y, e of x into e of y can be also written as x complement y complement. E of x is equals to x complement e of y is equals to y complement minus x complement y complement, which will be equals to 0. Okay, but the converse is not equal, not a true value, right? So coming to the next one, if x and y are two random variables, variable of x plus y is equals to variable of x plus variable of y plus 2 into c of xy. So we need to prove this. So if x and y are two random variables, we know that variance of x, that is sigma x square, is equals to e of x square minus e of x whole square. See here, జాగ్రత్తగా గమనించండి. See here, e of x square minus e of x whole square. See the difference, there is a difference between these two things. See here, this one is different from this one. Okay, then variance of x plus y is equals to e of x plus y whole square, x plus y whole square into e of x plus y whole square. Here we don't have a square for e, here we have square for both e and x plus y. So then we can written as e of x plus y whole square can be written as x square plus y square plus 2xy minus of e of x plus y whole square can be written as e of x plus e of y whole square. Okay, then it can be written as, so by taking individual expected values, that is e of x square plus e of y square plus 2e into x plus xy minus e of x square minus e of x square, okay, minus 2 into e of x into e of y. Okay, so e of x square as it is minus e of x square, we have what to call, we have arranged them in an order. So e of x square minus e of x square plus e of y square minus e of y square plus 2 into e into xy, have taken common these two, between these two terms I have taken 2 as common, 2 into e of xy minus e of x into e of y. So this will be 0 and this will becomes, okay, this will becomes sigma x square plus sigma y square plus 2 into cxy. Okay, see here we have wait a minute. Okay, see here e of x square minus e of x whole square, so it can be written as sigma x square, and this one e of y square minus e of y whole square can be written as sigma y square, and this value will be written as 2 into cxy. Therefore variance of x plus y is equals to variance of x plus variance of y plus 2cxy, 2 covariance of x and y, and okay, so hence we have proved that one. Okay, we'll go for the next one. See here, if x and y are two random variables, then the covariance of x plus a and y plus b, where a and b are constants, is equal to the covariance of, we need to prove that, is equal to covariance of x plus a comma y plus b is equals to covariance of x comma y, which will be equals to cxy. We need to prove that one. So see here, what they have taken, if x and y are two random variables, then covariance of x plus a and y plus b can be written as expected value of, covariance of x comma y can be written as expected value of x minus x complement into y minus y complement. Let it be x and let it be y. Okay, so let it be this here, this is x and this is your y. So covariance of x comma y can be written as e of x plus x minus x complement and sorry, e of x minus x complement into y minus y complement. So we can write like this, e of x plus a minus e of expected value of x plus a minus x complement minus a into y plus b minus y complement into b. Okay, so here minus the multiplication is covered, minus x complement minus into plus minus a Okay, next y plus b minus y complement minus b. So this can also be written as here x, sorry, a and a, b and b are gets cancelled. That means expected value of x plus x complement into y minus y, sorry, expected value of x minus x complement into y minus y complement. Hence we have proved, which will be equals to c of xy, which will be equals to c of, sorry, c of x y. So we need to prove that, right? Covariance of x plus a comma y plus b is equals to covariance of xy, that is equals to c of xy. Okay, coming to the next one. If x and y are two random variables, then the covariance of ax by, where a and b are constant, then see there is a slight common thing here. So they have taken x plus a comma y plus b. Here ax plus ax and by, they have product, they have their product right now. Okay, see here constant. I repeat the statement. If x and y are two random variables, then the covariance of ax comma by, where a and b are constant, is covariance of ax by is equals to ab constant letters into covariance of xy, which can be written as ab into cxy. We need to prove that one. Since if x and y proof, see the proof. If x and y are two random variables, then covariance of ax minus ax comma by, covariance of x comma y is equals to what we can, x comma y can be written as x minus x complement into y minus y complement. We have written like this one. Covariance expected value of ax minus ax complement into by minus by complement. So here I have taken this a as common in this two one, and in these two things I have taken b as common, that is expected value of a into x minus x complement into b into y minus y complement. So we can write like this: e of ab into x minus x complement into y minus y complement. Therefore ab can be written in the here itself, which will be equals to ab small ab into expected value of capital X minus x complement into capital Y minus y complement. So which will, this will be equal, e of x minus x complement into y minus y complement will be equals to c of xy, covariance of xy. So into AB, I have written here. Okay, that is what we need to prove. See here, covariance of ax by, which will be equals to AB into covariance of x and y. It can also be written as AB into cxy. Okay, so this is the last property. See here, if x and x, y, z are the three random variables, then we need to find the covariance of three random variables. We have, till now we have seen only two random variables. We need to, now we are considering three random variables, two random variables only, but different way. X plus y comma z is equals to covariance of xz plus covariance of yz. Okay, see how it can be done. Sorry, we know that covariance of x plus y comma z will be equals to, we have written, see, a comma x comma y is equals to x minus x complement into y minus y complement. Okay, so this one can be written as e plus x plus y into x plus y whole complement into z minus z complement. So it can also be written as e of x plus y minus x complement minus y complement into z minus z complement. Yeah, I have multiplied this value with minus. That will be equals to the expected value of x plus y minus into plus minus x complement minus into plus minus y complement into z minus z complement. So can I write like this: e of x minus x complement plus y minus y complement into z minus z complement. See, there is a difference between these two things, this one and this one. See, just I will repeat that one. See here, they have given we need to find the covariance. So we need to show that covariance of x plus y comma z is equals to covariance of xz plus covariance of yz. So we, as we know that we have taken this one, and we have to prove this one. So by taking LHS, covariance of x plus y minus z is equals, x plus y comma z is equals to E of x plus y minus x plus y whole complement into z minus z complement. We have only one thing here, that's why we have written, we don't have any expression, that's why I have written like this, z minus z complement. So multiply this one with your negative sign, that can be written as expected value of x plus y minus into plus minus x complement minus into plus minus y complement into z minus z complement. So we can also write this one as e of x plus capital X minus x complement plus y into y minus y complement into z minus z complement. So by multiplying this one, okay, we have to multiply z minus z complement with both these two things. Then expect e of x minus x complement into z minus z complement plus e of y minus y complement into z minus z complement. We can also write write this one as covariance of xz and this one as covariance of yz. Hence we have proved what they want to show us. Okay, thank you.
Was that audible? Was that audible?
Yes, sir.
Okay, is it clear? Voice clear గా ఉంది.
Yes, sir.
Yes, sir. Only
Okay. Probably from tomorrow onwards, your classes will be like that. Okay, and you can find these classes, all the previous classes also in Google. Your DBS Talks. Okay. సో రేపు క్లాస్ ఉందండి.
DLD class ఉంది సార్.
ఎన్నింటికమ్మా?
సార్ మార్నింగ్
ఫస్ట్ అవరా?
సెకండ్ అవర్ సార్.
సెకండ్ అవరా? సరే. ఓకే, రేపు డిఈఎల్డి సెకండ్ అవర్ ఉంది కదా, ఐ థింక్ కంప్లీట్. ఓకే, నో ప్రాబ్లం సరిపోతుందండి. మిగతా వాళ్ళకి ఇన్ఫార్మ్ చేయండి. I have strict instructions from the university to send your online opinions. ఫోన్ లేదు, సిగ్నల్ లేదు, మేమేం చేయలేం. ఓకేనా? ఒకసారి మీ ఫ్రెండ్స్కి ఇన్ఫార్మ్ చేయండి, క్లాసెస్ జరుగుతున్నాయి కదా, ఇన్ఫార్మ్ చేయండి.